You ever find yourself fiddling with, like, a car battery that's gone dead? Or maybe just staring at your power bill thinking, what am I actually paying for here?
Hmm.
We all use electricity, this invisible force, all the time. So in this deep dive, we're going to try and crack open the basics, the fundamental laws, the bits and pieces that make it all tick.
Exactly. And we've got some great source material for this. Basically, a set of key questions and answers about electricity.
Right.
Think of it as taking the mystery out of it, from, the simplest circuit lighting a bulb right up to the difference between the power from a wall socket and what's inside a battery.
Yeah, our mission here is really just to pull out the essential stuff, the things that hopefully give you those aha moments without, needing a PhD in electrical engineering.
Absolutely. Just a solid, practical grasp.
Okay, so let's jump right in. Where do we even start? What's the absolute cornerstone concept we need to get?
Well, without a doubt, that's Ohm's law. It really is the bedrock. It explains how voltage, current, and resistance are all interconnected in a circuit.
Ohm's law. Okay, I-E-R. I remember that from school, kind of. But what does that actually mean in practice? What are I, E, and R?
Okay, let's break it down. So I is for current. Think of that as the flow, the actual movement of electrons through a wire.
Like water in a pipe?
Sort of, yeah. It's measured in amperes or amps. Then E is voltage. That's the push, the electrical pressure driving those electrons, measured in volts.
Okay, pressure.
Then R is resistance. Just like it sounds, it's the opposition to that flow, whatever's slowing the electrons down. That's measured in ohms.
So voltage pushes, current flows, resistance resists. Makes sense. It's a relationship then. What happens if you, say, turn up the voltage, the E, but the resistance, R, stays the same?
Exactly. That's what the law tells us. Our source material really highlights this direct link. If you increase the voltage, the push and the resistance doesn't change, then the current I has to increase proportionally.
More push, same bottleneck, means more flow.
Precisely. Think about a dimmer switch on a light. You're basically adjusting the voltage. Turn it up, more voltage, more current flows through the filament, and the light gets brighter.
Okay, that clicks. So this voltage, this electrical push, where does it actually come from? What are the main ways we generate electrical energy?
Well, our sources point to four main categories. First, there's mechanical generation. That's using something like a generator to convey physical movement, like spinning into electricity.
So hydro dams, wind turbines, that sort of thing.
Exactly, that's mechanical. Then there's chemical, the most common example, a battery.
Right.
Chemical reactions inside create that electrical pressure, that voltage.
Okay, mechanical, chemical. What else?
Photoelectric, that's converting light directly into electricity. Think solar panels. Certain
Yeah.
materials just do that when light hits them.
Capturing photons, basically.
Yeah.
Cool. And the last one.
Thermal heat, you can actually generate a current from a temperature difference between 2 points using certain devices. It's maybe less common on a large scale, but it's another source.
Wow. Okay, so spinning things, chemical reactions, sunlight, even heat differences.
Yeah.
Lots of ways to get that initial push.
Yeah.
Now, once we have that energy, how does it actually, do something useful?
Yeah.
That brings us to circuits, right?
Absolutely. A basic DC circuit direct current, like from a battery, needs three essential things. First, you need that source of electrical pressure, the voltage source. Engineers might call it EMF, electromotive force, your battery, basically.
Got it.
Second, you need resistance. This is the thing that actually uses the energy. A light bulb filament, a motor winding, whatever's doing the work.
The energy-consuming device.
And third, you need conductors. These are the pathways, usually copper wires, that let the electrons flow easily from the source through the resistance and back to the source again. It has to be a complete loop.
Right, a closed path. Source pushes electrons. They do work in the resistor. They flow back. Simple enough for DC. But then there's AC, alternating current. The stuff from the wall sockets. That feels, I don't know, a bit trickier.
It does add a few more layers, yeah. AC circuits have some extra concepts. One big one is capacitance. That involves a component called a capacitor. Sometimes people call it a condenser, an older term.
Capacitor, okay.
Yeah.
What's its role? What does it do in an AC circuit?
Its main job is to store electrical energy, but it stores it in an electric field. Think of it like a very small, very fast-acting, rechargeable battery or reservoir within the circuit.
Stores energy temporarily. Okay.
It can charge up and discharge, and that really affects how the current and voltage behave over time, especially since AC is constantly changing direction. Then there's also inductance.
Inductance.
It
That
is.
sounds related to induction.
It is. When alternating current flows through a coil of wire, It creates a changing magnetic field around the coil. And that changing field actually induces a voltage back into the coil itself. And this induced voltage opposes the original change in current. It's like the circuit has electrical inertia. It resists changes in the flow.
Okay, so capacitance is like temporary storage, inductance is like inertia, pushing back against change. Our notes also mentioned impedance for AC. What's that?
Impedance is basically the total opposition to current flow in an AC circuit. It's a broader term than just resistance
Broader how?
because it includes not only the simple resistance, like in DC, but also the effects of capacitance and inductance. Those effects are called reactance, capacitive reactance, and inductive reactance. So impedance bundles all three together to give you the overall opposition in an AC circuit, which can change depending on the frequency of the AC.
Right, gotcha. So AC is definitely more dynamic. Okay, let's switch back to something maybe simpler. Power. How much work is actually being done? How do we measure electrical muscle?
In a DC circuit, the unit of power is the watt, and the formula is pretty straightforward. Power, we use P for that, equals current I times voltage E. So P equals IXE.
Watts. We hear that all the time. Light bulbs, appliances.
Exactly. And our source gives a nice comparison. 746 watts is about equal to 1 horsepower.
Oh, that's useful. Puts it in perspective.
Gives you a feel for it, yeah. So if you see a motor rated in watts, you can kind of translate it back to horsepower in your head.
And when we talk about larger amounts of power, like a whole house's usage.
Then we typically use kilowatts. Kilo just means 1,000. So 1 kilowatt is 1,000 watts. That's the unit your electricity meter usually measures.
Okay. Kilowatt hours on the bill, right?
Precisely. Power used over time.
Got it. Now back to DC circuits for a second. The material mentioned 3 types, series parallel and series parallel. Can you give us the quick difference?
Sure. In a series circuit, everything is connected in a single line, one after the other, like cars on a one-lane road.
So the current has only one path.
Exactly. If there's a break anywhere in that path, like one bulb burns out in an old string of Christmas lights, the whole circuit stops working.
Okay. And parallel.
In a parallel circuit, components are connected across multiple branches. So the current splits up and has different paths it can take. Think of it like a multi-lane highway.
So if one bulb burns out,
the others on different branches stay lit because the current still has other paths to follow back to the source.
much more convenient for Christmas lights. And series parallel.
Just a mix of both. You might have some components in series within one branch and then multiple branches connected in parallel. It's just combining the two configurations.
Okay, different ways to wire things up depending on what you need. Now, let's dig into batteries. We all use them. The source material talks specifically about lead-acid batteries. What are the key takeaways there?
Well, it uses a 24-volt lead-acid battery as a common example. It explains that this type of battery is usually made of multiple individual cells connected together.
How many cells?
Typically, for a 24-volt battery, it would be 12 cells connected in series. Each lead-acid cell produces about 2 volts when fully charged.
So 12 times 2 volts gives you the 24 volts total. Makes sense.
Exactly. And a really critical thing with lead-acid batteries is the electrolyte. That's the liquid inside, usually sulfuric acid and water.
Right. What about it?
Its specific gravity, which is basically its density compared to pure water, tells you directly about the battery's state of charge.
House.
As the battery discharges, the acid gets used up in the chemical reaction, and the electrolyte becomes more like water, so its density decreases. When you recharge it, the process reverses, and the density increases again.
Okay, so density equals charge level, roughly. What should it be for a charged battery?
For a fully charged lead-acid battery, the specific gravity should be somewhere between 1.275 and 1.30.
And you measure that with?
A tool called a hydrometer. It looks a bit like a large eyedropper with a float inside. You suck up some electrolyte, and the float sinks to a level corresponding to the specific gravity, which you read off a scale.
Simple enough. But here's a really interesting point from the source. You can't use a hydrometer on a nickel-cadmium or NiCad battery to check its charge. Why not? That seems counterintuitive.
It's a super important distinction. It comes down to the chemistry. In a NiCad battery, the chemical reactions that happen during charging and discharging don't significantly change the specific gravity of its electrolyte.
So the density stays pretty much the same whether it's full or empty.
Exactly. So sticking a hydrometer in there won't tell you anything useful about the charge level. You need other methods, usually measuring the voltage, for NiCad batteries.
That's a great practical tip. Good to know. The source also mentions temperature affecting hydrometer readings for lead acid.
That's right. Temperature changes the density of liquids. So if the electrolyte is really hot, say above 90 degrees Fahrenheit, or really cold, below 70 Fahrenheit, the reading on the hydrometer won't be quite accurate for indicating the charge state.
So you need to adjust.
Yeah, you need to apply a temperature correction factor to get the true specific gravity reading. Most hydrometers or battery manuals provide charts for this.
Okay, good detail for anyone doing maintenance. What else does the source say about taking care of these lead-acid batteries?
Maintaining the electrolyte level is key. It needs to cover the plates inside. The guideline is usually about 38 of an inch above the tops of the plates.
And if there are baffles?
Some batteries have baffle plates near the top of each cell to prevent splashing. In that case, you fill it just up to the little indicator hole in the baffle plate. Don't overfill it.
Right. What about corrosion? Battery terminals always seem to get fuzzy green stuff on them.
Yeah, corrosion is a big issue. The acid fumes are corrosive. The source recommends cleaning terminals regularly and protecting the battery compartment itself, often with special coatings like bituminous paint, which resists the acid.
Makes sense. And one more battery point, storing NiCad and lead-acid batteries together. Bad idea.
Very bad idea, according to the source. They should be stored separately.
Why is that?
The fumes from a lead-acid battery can actually contaminate the electrolyte in a NiCad battery. This contamination can mess up the NiCad's chemistry, potentially damaging it or reducing its performance and lifespan. So keep them apart.
Okay, really useful battery specifics there. Let's shift to another fundamental idea. Electromagnetic induction. What is that, in simple terms?
Electromagnetic induction is this really cool phenomenon where you can generate an electrical current in a wire just by changing the magnetic field around it. You don't even need to touch the wire.
Changing magnetic field creates electricity.
Yep, and our source material explicitly states this is the principle behind how transformers work.
Transformers, the things on power poles and in device chargers.
Exactly. They use electromagnetic induction to efficiently change AC voltage levels, stepping voltage up for long-distance transmission and then down again for use in homes and devices. It relies entirely on that link between electricity and magnetism.
So no direct connection needed, just the magnetic field bridging the gap. Clever. Now, thinking bigger picture, power systems. The source mentions paralleling generators. What's the point of running multiple generators together?
Paralleling generators just means connecting two or more of them so they feed power into the same electrical system, sharing the load.
Why do that?
Couple of main reasons. One is capacity. You can supply more power than a single generator could alone. The other, maybe more important, is reliability and redundancy.
Like a backup.
Sort of. If one generator needs maintenance or fails, the others can pick up its share of the load, so the power supply isn't interrupted, or at least the interruption is minimized. It makes the whole system more robust.
Okay, sharing the work and providing backup. Makes sense for critical power needs. Lastly, there's a mention of a no-trip or trip-free circuit breaker. What's special about that?
A trip-free circuit breaker is a safety design. Like any breaker, it opens the circuit if it detects an overload or a short circuit.
Right, stops the current.
But the trip-free part means that you physically cannot hold it closed or reset it manually as long as the fault condition that caused it to trip still exists.
So even if you try to flip the switch back on?
It won't stay on. It'll just keep tripping immediately until the underlying electrical problem, the overload or short, is actually fixed.
That sounds like a crucial safety feature, especially somewhere you can't easily troubleshoot, like maybe an airplane mentioned in the notes.
Exactly. It prevents someone from inadvertently forcing power back into a faulty circuit before it's safe.
Huh.
It prioritizes fixing the root cause.
Got it. Okay, that's a lot of ground covered. Let's maybe try and summarize the key takeaways from this deep dive into electricity fundamentals.
Sure. We kicked off with Ohm's law, that vital I equals ER relationship governing voltage, current, and resistance. That's really central.
Yeah, the foundation.
Then we looked at the four main ways we actually generate electrical energy: mechanical, chemical, photoelectric, and thermal.
Where the power comes from.
We broke down the essentials of a basic DC circuit: source, resistance, conductors, and then dipped into AC, adding capacitance, inductance, and the idea of impedance as the total opposition.
Right, the AC complexities.
And measuring power.
Measured in watts, calculated as P parallel XE in DC.
Right.
And we use kilowatts for larger amounts. We also briefly touched on the different DC circuit types: series parallel and series parallel. And then the big dive into batteries.
Focused on lead acid, understanding specific gravity, using a hydrometer as a charge indicator.
And crucially, why that doesn't work for NiCad batteries.
Exactly. Plus maintenance tips like electrolyte levels, corrosion prevention, and keeping lead acid and NiCad batteries stored separately.
Then we hit electromagnetic induction.
The principle behind transformers transferring energy via magnetic fields. And we covered paralleling generators for reliability and load sharing.
And finally, that safety feature of trip-free circuit breakers that won't reset until a fault is cleared.
Yeah, I think hitting those points gives you a really solid grasp of the essential electrical principles we aimed for.
Absolutely. And like we said, knowing this stuff isn't just abstract theory. It really helps make sense of the tech that powers our world. So maybe a final thought to leave folks with. We talked about different ways to generate power spinning turbines, solar panels, batteries. Knowing these fundamental laws we've discussed, Ohm's law, induction. What do you think the next big shift or breakthrough in power generation might look like? And how does understanding these basics help us even think about that future?
That's a great question, something to definitely ponder.